Welcome, everyone. Thank you for joining us for today's webinar. My name is Catherine Ely, and I will be your host. Founded in 1988, INO is the largest center of expertise in optics and photonics in Canada and is among the best technological research centers in the world. With over 184 employees, we are located in Quebec City, Canada, with an office in Hamilton, Ontario as well. Our mission is to bring to life innovations that enable the industry from all over the country to be more productive and competitive. Today's webinar will be recorded and available on our website in the resource section. We have 45 minutes scheduled for today, including question and answer. Please type any questions you have into the Q&A box during the presentation. At the end, we will ask as many questions as we can in the time allowed. Throughout the presentation, we will also have 2 polling questions. Our topic today is advances in polarization maintaining active fibers, high power, beam quality, and reliability. Our presenters today are David Melasson, Solutions Manager, and Antoine Preux, Technical Director for our Industrial Solutions team. David and Antoine, thank you for your time today. David, why don't you go ahead and get us started?
Thank you, Catherine. Now, before we jump into the main subject, I would like to give you just a little bit of color on INO's position. And the first thing to know is that there is a wide range of expertise at INO, from optomechanical to microfab, lasers to electronics, from systems engineering to artificial intelligence. INO is home to world-class researchers from various fields, and that enables solutions with a 360-degree point of view. Our approach to innovation covers the whole spectrum, from analysis to scaling up. And partners can get inserted anywhere in the process, so we will accompany you wherever you are in the process. Today's topic is centered on one of our historical strengths, erbium doped fibers and lasers. INO has been developing and manufacturing fibers for over 30 years now, with the goal of finding the perfect balance between high power, beam quality, and durability, a very important factor in the economical viability of the final product.
So we'll begin with a quick poll question. So our first poll question is, what is your field of application? A, biomed tech, B, aerospace, C, defense, D, industrial, or E, other. If you select other, please feel free to specify in the chat. So I will close the poll. And it looks like the majority of you responded industrial. Thank you very much for sharing.
Okay, now let's dive into our main topic. Without a doubt, we're in a world where technology is ever present. I'm sure everyone is aware of that. It is seen as the solution to many problems, whether in industrial activity in terms of productivity, environmentally for capture, cleaning, or clean generation, economically for new platforms or products, or even socially through communication and AI. Semiconductors and electronics have been a wonderful platform for technological development for the last 50 plus years. Computer age, telecommunications, space activity. However, we start to see limits a little more clearly now through energy consumption, interference, transmission losses, manufacturing boundaries, just to name a few. Now, if we shift our attention to the optics photonics industry, we see a path forward and an enabler for the next wave of technological evolutions. Quantum, we can think of cryptography, key distribution, computing. Artificial intelligence, communication, biomedical, security, ideas abound. With such ideas and new opportunities, it's time to think about what tomorrow could look like. We can now think of new tools, and here are some examples. Ultra-fast pulse laser for heat-affected zone control, and therefore better surface treatment, where a reduced heat-affected zone can minimize impact of an incision or improve geometry of material ablation. Frequency conversion. We can create laser sources to support high-precision manufacturing. Wavelength down conversion to provide needed inspection accuracy, or longer wavelengths to process new materials. Directed energy, whether for laser fusion, allowing ever greater distances to enable space communications, even for security purposes. Energy levels unimaginable not so long ago can now be conceptualized with beam combining and can enable such development. And micromachining, lasers definitely can be an integral part of tomorrow's industrial effort. Now, for realistically applicable and profitable technologies in today's world, we must overcome a certain number of challenges, especially associated with high power levels, and based on utilization of available and affordable silica glass fibers. Most of the novel applications we can think of imply high power levels, which brings its own challenges. First challenge, pretty obvious, power density. Non-linear behaviors are inevitable when increasing power for laser applications. And depending on the laser mode, either pulsed or continuous wave, the order of importance or appearance of the elements above will differ. Second challenge, beam quality. If we go back to the basics, a laser is fundamentally a very well-controlled energy source. And M-square measures that beam quality compared to a perfect Gaussian beam. It's an essential element in many high-power applications. TMI will have an impact, and there are other elements of the fiber, doping, profile, geometry, potentially impacting beam quality. Third challenge, photodarkening, which is due to continued exposure to radiations, and eventually will lead a fiber to be unusable. It's important to note that when the first steps towards higher laser power were successfully addressed at the start of the 21st century, it quickly put emphasis on photodarkening, which became one of the most crucial aspects for optical fiber manufacturers to solve, at the risk of becoming irrelevant. Now that we have seen the opportunities and challenges, comes the hard part of exploring and solving. The next sections will be covered by my colleague and technical director, Antoine Proux. But first, let me hand it over to Catherine.
Thanks, David. So we'll ask our second poll question, which is, which of the following perimeters is the most important for your laser design and application? A, low nonlinearity, B, high beam quality, or C, high resistance to photodarkening? So I will now close the poll. And the majority of you responded high beam quality. So now I will pass over to my colleague, Antoine.
Hello, thank you, Catherine and David. So as David mentioned, when we wanted to address the market of ytterbium doped fibers that were PM for pulse operation, there were four main features that were required. As mentioned, we needed to mitigate the nonlinear effects, so large mode area fibers were obviously needed. We wanted to offer very high beam quality, so that meant that good control on the refractive index profile of the core was important, and we also needed some strategies to enhance the filtering of the higher order modes. And as mentioned also, the photo darkening resistance was a key issue a few years ago, and when we designed our next generation, when we were thinking about what should be the next generation of large mode area fiber for INO, photo darkening resistance was, of course, very important. And since we are mainly addressing the pulse laser market, polarization maintenance was very crucial as well. So basically, what is important to find here is these four main features that we were after. They must be treated or addressed as a whole, because you can imagine that if you find a solution or a strategy to address one of these, then it can be detrimental to another one. So they must not be addressed independently, but more seen as a whole. And I will show here how they can influence or how they can depend on each other. So firstly, if you look at the low nonlinearity versus high beam quality issue, well, of course, there's no way around it. If you want low nonlinearity, you need a large mode, so a large mode area fiber. But as you increase the core size, you will support more and more modes. So it's important to have some strategies to filter out the high order modes and keep the fundamental mode and amplify it to high power. So I will have a few slides later on what the strategy that INO has developed are. Now, another aspect is, as we mentioned, the low photo darkening, and we need to be careful here because it's clearly the photo darkening is addressed by the core composition, and there are some. When we addressed when we looked at the issue, there were some core compositions that were known and that. But they were not all equal in terms of achieving high beam quality. So the first one was the phosphosilicate glass matrix. So this one was extremely interesting because it can also be seen as even photo darkening free. So it's in terms of resistance to photo darkening, the phosphosilicate is probably the highest performer. However, it is usually associated with very important center dip. So if we are after a very high beam quality, so very low M square fiber, then we can run into some complications. Another strategy was cerium co-doping that was quite popular, and it gave quite good results. But often there was a high delta N in the core, so that was associated with adding dopants like this. So if you need to keep the numerical aperture of the core limited, then you probably need to think about co-doping with other dopants like fluorine to reduce the index. So it adds some complication. And another core chemistry that was interesting is the phosphoaluminosilicate composition. And this one is particularly interesting because depending on the ratio of phosphorus and aluminum, you get the formation of AlPO4 compounds, which are known to significantly reduce the delta N of the core. So that can be advantageous. So I will come back to this. Yeah. Now, the other aspect is since we wanted to have only polarization maintaining fiber, it's crucial to find a core composition that will be, yes, low photo darkening, but that will also not lead to very high internal stress in the preform. because as you may know, when you need to have a PM fiber, you need to typically drill the preform to insert the stress rods. So if you have a very stressed mother preform, then you can run into problems if you want to drill it to transform it into polarization maintaining fiber. Now, so based on this, after the careful review of the pros and cons, we did a lot of literature review and we did a lot of testing also. And it turned out that for our needs, so for the type of fibers that we wanted to develop and offer on the market as our next generation of PM ytterbium dope fiber, we found out that for us, the ytterbium phosphoaluminosilicate was probably the best candidate. Well, as we just mentioned, we were expecting a low level of photodarkening, maybe not the absolute best resistance to photodarkening, but good enough to keep a good control on the refractive index profile and a good photodarkening resistance. It's also we view this core composition as being very advantageous for offering a low core delta N, because this will be it would be compatible with INO's proprietary triple clad and multi-clad design that I will touch in in the next few slides. These are strategies to enhance the higher remote filtering, and this was seen as being very advantageous for us. And also this low core delta N or this core chemistry, we expected that there would be no big issues for the drilling of the preform for the PM transformation. So that was a crucial aspect as well. And also, it was known that for this core chemistry, there was a very limited center dip to be expected. So we were expecting to be able to achieve a very good control on the refractive index profile. So all in all, what this means is that this ytterbium phosphoaluminosilicate for us appeared to be the best balance between the refractive index control versus manufacturability versus photodarkening resistance. So this is why we chose this one for our next generation ytterbium dope PM fiber. Now, we have discussed about the core composition and why we chose this way, this thing, but there were other features that were needed. And we mentioned that high beam quality was very important. And to achieve this, it's important to have strategies to filter out the high order mode. So in the next couple of slides, I will run you through the INO technology for regarding this. So let's first start about the very standard double clad fiber. So I'm pretty sure everybody in the audience is aware of what it is. It's the simplest form of fiber where you have a standard step index core surrounded by pure silica cladding. Now, if you want to have a large mode area, you need, of course, to limit the numerical aperture of the core. So one way to do this is to co-dope the core to limit the refractive index increase due to the presence of dopant. Now, what INO has done, and we have a patent on this, is the triple clad design. So this is quite a simple strategy. So instead of co-doping the core with a dopant to reduce the index, we dope the cladding to raise the index of the cladding and effectively reduce the core delta N. So that's interesting. That works quite well, but you have to expect similar performances to a double clad fiber. There's no real advantage in terms of filtering performances. It will be the same as a double clad. So what INO has come up with and patented is what we call the multi-clad design with the depressed cladding. So what this is it's basically another variation of the triple clad, where you take the basic triple clad refractive index profile of the whole fiber, but you add a lower refractive index ring between the core and the raised index cladding. And I will have a few slides explaining how this works. But this, dramatically improved the high order mode filtering. And also another trick that we have in our multi-clad design is what is called the selective doping or the confined core. And what this is it consists of a passive ring around the ytterbium doped region in the core. And this passive ring has the same refractive index level as the ytterbium doped region. So what this does is it increases the overlap between the active region and the fundamental mode. So it will, as the signal gets amplified along the length of the fiber, you will have preferential amplification for the fundamental mode compared to the higher order modes. Okay, now that we've seen what the depressed cladding is, now I want to touch a little word about how it works. So, so as mentioned, the idea is to use this technology to obtain high beam quality, so very low m squared, and the idea is to filter out preferentially the high order modes through coiling. So you have on the left figure here a schematic view of what the core profile looks like. So you see here on the pink area, this is it represents the area that is doped by with the ytterbium and the other co-dopants. Just surrounding this pink region, you see at the same index level, you have the confined core. And then surrounding the core, you see that there is some kind of a trench. So this is what is called the depressed cladding. And this depressed cladding is positioned between the central core and the raised index cladding. So the idea here is that when you carefully engineer the depth and the thickness of this depressed cladding ring surrounding the core, you can engineer it to have a very good confinement of the fundamental mode at a certain coiling diameter. But then the higher order modes that are also supported by the core, they will have their evanescent wave touch. So they will experience the presence of the raised index cladding, and what it will do is it will make them leaky. So for the optimal coiling diameter for this guiding structure, you will have very good confinement of the fundamental mode, but very leaky propagation for the higher order modes. So so I know we have a patent on this technology, and it works quite well. So now, if we look a bit, if we dig a bit deeper in what it does. So yes, it does improve the differential bending losses between the fundamental and higher order mode, as I just explained. But also, one very key aspect of this is it really provides some flexibility on the coiling diameter, on the optimal coiling diameter for this particular fiber. And this is becoming particularly important as you scale up the core diameter, because I mean, for large mode area with limited core size, the step index and double clad fiber works quite well. But as you increase the core diameter to 30, 35, 40 micron, then it will become, you will run into some issues to work with this fiber very well. So to explain this, here on the right, you have the top figure. You see these are simulations for a standard double clad fiber with a 35 micron core. So what you see here, the blue curve is the attenuation of the fundamental mode as a function of the bending radius of the fiber. And the red curve is the same thing, but for the first higher order mode. So you can see here in the sort of shaded region that the window of acceptable bending radius to have good filtering is very narrow. So I mean, we can expect that the laser engineers having to design an amplifier will run into issues, because you can expect that maybe some differences from batch to batch of a same fiber model maybe will lead to slightly different optimal bending radius. So, I mean, this is not really usable. So it's we really needed to, if we want to increase the core size, it's important to have another strategy to have more usable bending radius. So this is exactly what the depressed cladding does. So as you see on the lower figure, it's the same simulation, but this time with an engineered depressed cladding to optimize the differential bending losses. And you can see on this figure very well that it significantly broadens the window of usable coiling diameter. So in this case, you can expect to be able to coil the fiber from maybe 6 to 10 centimeter in radius and still have adequate filtering. So the message I want to pass on here is that this depressed cladding is not only good for differential bending losses, but it can be really seen as a new degree of freedom in fiber design in order to design the fiber to have a specific and optimal coiling diameter within reason. Of course, there are limits that we must stay within, but still it's a very interesting fiber design tool or lever, I would say. Now, we have discussed about the different building blocks for our next generation ytterbium doped PM fibers. We talked about the core composition for low photodarkening behavior. We also talked about the multi-clad and depressed cladding for enhanced differential bending losses. So now, how did this turn out into the fiber line that Aino is offering right now? So this is what we will see on the next slide. So what we came up with based on these choices is what we call the fast fiber series of fiber for pulse lasers. So the fast fiber is actually a complete family of ytterbium doped PM fiber that are low photodarkening and are all designed to have a very low m² output. So you see on the top right figure here, this is the family picture, I would say. So it starts at the left with the first low photodarkening fiber that I know has commercialized. So it's the YB401 PM. So that's a very simple step index, single clad 5125 PM fiber. And then we also have 10125, 15125, and then more in the large mode area side, we have 35 to 50, 40 to 50, and the tapered fiber, which is a fiber with a 56 micron core output that can deliver very high beam quality as well, despite the large core size. So basically, the idea with this fast fiber family is to have a fiber suitable for any amplification stage that a customer may need. So I will not go into all the details of the figure at the bottom of the the slide. But for example, here you can imagine this is like a laser chain that we've worked with at INO, and this is well a simple seed laser that is first amplified through a preamp consisting of YB401 PM fiber. Then there's a booster amplification stage using 10125. And then there's the final power amplifier, in this case using the tapered fiber with a 35 micron input and 56 micron output. So I will not discuss today about the smaller core fiber. I think the interesting thing to discuss here today is really about the large mode area fibers. So I will discuss mainly about the 40 to 50 and the tapered fiber. The 35 to 50 is quite an interesting fiber as well, but it's very close to the 40 to 50. So it would be a bit maybe redundant to go in details for both of them. So I think I will go through the specifications and performances of the 40 to 50 and the tapered fiber in the next few slides. Okay, now this first one, this new, it's a very new fiber. It's I would say it's our new baby. It has been launched this year at Laser Munich 2025. So it's a fiber having a 40 micron core diameter, 250 micron cladding, a core numerical aperture of 0.07. Of course, it's PM, and it has an absorption of about 12 dB per meter at 976, and it is designed to offer a very low M squared. So the specification is an M squared lower than 1.2, but this is I would say conservative. It's you can achieve better than this routinely. And this fiber, and this is very important, it's designed to have an optimal coiling diameter between 18 to 20 centimeter. Now, to give you an idea of the long-term reliability that is to be expected with this fiber, we did run a test for over 1,000 hours at an average power of 100 watt. And in this case, it was in pulse regime, so it was 400 kilohertz, 2.5 nanosecond, and it was counter pump in that case. And you can see here on the graph that we have observed less than a 1% variation in output power over 1,000 hours, and the optical efficiency remained unchanged throughout the test. And also we have monitored the beam quality. So you can see here the near field beam profile also remained essentially unchanged for the entire duration of the test. I think these are results that are quite interesting and can give a good idea that this fiber can be operated at high power in pulse regime very reliably for quite a long time. Yeah, and also a topic of great interest these days and for the past few years is the TMI threshold. Usually when we operate in pulse regime, usually we are well below the TMI threshold in most scenarios, but still it was a very relevant measurement to make. So that's why we did it, and you can see here the result. In this case, it was in QCW and in co-pumping configuration, and we have been able to demonstrate that the TMI threshold for this 40 to 50 fiber is easily above 300 watts. So you see here it's maybe 370 or so that we can clearly see strong degradation of the m squared as the power increases. So we are quite satisfied by this. We think it's quite an interesting result, and for the intended application of this fiber, the TMI threshold should not be an issue. But it was quite interesting to measure it and to communicate it with all of you today. Okay, so that's it for the 40-50 fiber. Now, I want to touch a word on the INO tapered fiber, which we could say it's probably the flagship of the fast fiber line. So this is not a standard fiber that you can typically purchase by the length. This tapered fiber is sold as a unit, so it consists of a straight section of 35-50 fiber that then tapers out to 56-400, and then there's a straight section of 56-400 fiber. So this is it's quite an interesting design. The idea here is to obtain the largest core possible for the output, while still being able to offer an effectively single mode operation. So it would not be really feasible to fabricate a straight 56-400 fiber and have good mode filtering and obtain a very low m squared output out of this fiber. So the trick that we have, what we are doing here, is to start with the 35-50 section with depressed cladding that is very efficient at filtering out the high order mode. And then in the first meter or so of propagation, the high order modes are filtered out, and then the fiber adiabatically tapers out to 56-400. And if the packaging is done correctly and there's no stress on the fiber, then the high order modes are not getting repopulated through the propagation and amplification in the fiber. And we are left with single mode output with very low m squared. So so that's so this fiber, it has a slightly lower absorption. It's at about 8 dB per meter at 976 nanometers. So at 915, this is a 2.2 dB per meter. And one important aspect in terms of packaging for this fiber is the recommended coiling diameter. So you can imagine that since the fiber diameter and core diameter changes along the length of the fiber, there is no single coiling diameter that will work. So the trick here is to package the fiber so that the 35-50 section is coiled at 20 centimeter to effectively filter out the high order mode. And then in the tapered region, it needs to be gradually coiled to a larger diameter, up to 40 centimeter. Now, maybe to touch a point here, if you can accept, because 40 centimeter is often rather large, and in some applications it's too large for to package the fiber. If you can accept slightly smaller effective area at the output, you can coil the 56-400 section to slightly smaller than 40 centimeter, but it needs to it should not go below the low 30 something, maybe 32 or so. But maybe that's it's a matter of testing on what you need for your operation, because you can imagine if you coil it to, let's say, 25 centimeter, then the mode will be so deformed and the effective area will be so reduced that you will lose the benefit of the large core. Now, again, to show the low photodarkening features or performances of this fiber. We ran a tapered fiber here at 150 watt for a QCW operation. And we observed that over about a year, so 8,000 hours, we observed less than 2% in reduction. So again, that's I think that's quite convincing that this fiber can be reliably operated at high power for and reliably. Yeah. And just like for the 4250, we measured the efficiency before and after this 8,000 hour test, and there was no difference between the beginning and the end of the test. So, yeah. Now, maybe the question that can be interesting about this tapered fiber. So what if we push it to the absolute limit? How far can we go in terms of average power and peak power? So we did this, and these most of these results have been presented in proceedings like for Photonics West in the past few years. So we used a three-stage amplification, as you see here, with a laser engine at the output for the power amplifier. And you can see on the table at the bottom that we have achieved an average power over 600 watt in CW. And in that case, that the limit was the TMI threshold that we had to stop the test at this point because the beam quality was dramatically degraded. But I mean, this fiber is not really intended for CW operation anyway. So if we look at the pulsed regime, so first in nanosecond, we reached an average power of 250 watt with 2.2 nanosecond pulses. So that represents an energy around the millijoule. So in this case, the stimulated Raman scattering was the limiting factor. And the story is quite similar in picosecond, where we reached over 275 watt for 35 picosecond pulses. In this case, we reached a peak power of 1 megawatt. And again, the main limitation was the Raman scattering in this case. So, of course, these are results when you push the fiber to the limit. So we do not recommend designing industrial lasers or amplifiers with these power levels in mind. These are it's not advised for long-term reliability, I would say. But it's still quite interesting to see how far this fiber can go. So thank you. That's what I had to present about the fast fiber line today.
Thank you, Antoine, and thank you, David. So we will now open the floor to questions. As a reminder, please type any questions you have into the Q&A box in your control panel. So I will just go and see. Our first question from the audience is how to determine whether the 35-250, 40-250, or tapered fiber is more suitable for my application.
Yeah, it really depends on what you need. Like, for example, if you need the absolute the highest level of peak power, quite probably the tapered fiber will be the best solution. So if you want to amplify rather short picosecond pulses, the tapered fiber is probably your best bet. However, if the beam quality is the most important thing, maybe you can expect that the 40-50 will lead to a slightly lower m square. I mean so it's easier, let's say, to get a 1.15 or so m square out of the 40-50 compared to the tapered fiber. And another aspect also, and it's often a subject that comes in the discussions with the customers, is the real estate available in the laser system. Because as we mentioned, the coiling, the recommended coiling diameter for the tapered fiber is 40 centimeter. So in some cases, it's not an option and it's too big. So in that case, the 40 to 50 can be very good also. And it should be noted also that there's the absorption of the 40 to 50 that is significantly higher than the tapered fiber. So we can use a shorter fiber length. So in that case, it helps limiting the B integral because it will be the 40 to 50 fiber will be shorter than the tapered fiber. So yeah, so for absolute highest peak power, probably the tapered fiber is the best bet. Otherwise, the 40 to 50 is a very interesting fiber as well. And the 35 to 50, this one, it's I would say the easiest one to package because the core is a bit smaller, so there's typically less mode mismatch with the commercial components like whether it's a combiner or mode fit adapter. So it's very easy to use. And yeah, so I would say for nanosecond pulses where the peak power may not be as high, the 35 to 50 could be the best option for picosecond, 40 to 50 or tapered fiber, depending on what are your limitations and requirements.
Great. Thank you, Antoine. And in the interest of time, I'll just take one more question. Is there anything distinctive about the small core non-LMA fibers in the fast fiber series?
The answer is it depends. There's the YB401 PM is a very interesting fiber. It performs very well. It has high absorption. It's 140 dB per meter of absorption. And it has very good performances in terms of photo darkening, but it is a step index fiber. Same thing for the 15125. This one has a low photo darkening chemistry, but it's a double clad fiber because for this core size, the depressed cladding was not required for effective filtering out of the high order mode. So, but however, that being said, there's the 10125 that is quite interesting. This one has some technology as well that and it's somewhat analogous to the depressed cladding, but the functionality is a bit different. So this could be the topic of another maybe webinar or technical note on this fiber. So this 10125, it has some dopants in the cladding and structure in the cladding to effectively pull the higher order modes away from the core. So the core is effectively single mode. So the cladding structure does not help to filter out the higher order modes because it's not needed, but it reduces the overlap between the cladding modes and the fundamental mode guided in the core. So it does in fact improve the beam quality at the output of this 125 fiber, and it's yeah. So if you're using 10125 fiber in your system, I suggest you contact me. We can discuss, and if you want to try this 10125, the performances are quite exceptional, I would say, in terms of beam quality. Yeah, so that's it. So distinctive, I would say the 10125 has something very distinctive, and the other two, they're very good for beam quality and photo darkening resistance, but they don't have as many features as the 10125 and the LMA fibers.
Wonderful. Well, thank you, David, and thank you, Antoine. And thank you to everyone for attending today's webinar. If you have additional questions or would like more information on our Fast Fiber YB Doped Fiber series for pulsed lasers, like Antoine said, please feel free to reach out to him. As well, if there were any questions that we did not get to in the chat today, we will follow up with you after the webinar. So once you leave today's webinar, a survey on the presentation will appear, and we would appreciate if you would take the time to complete it and provide your feedback. You will also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. So again, on behalf of Ino, David, Antoine, and myself, thank you for joining us today and enjoy the rest of your day.
Thank you very much.
Thank you.